Good afternoon. Welcome to Chemistry and the Next Generation Science Standards. My name is Joy Barnes-Johnson. I'm a teacher along with Linda Cody and Janine Giamenko at Princeton High School in Princeton, New Jersey. The three of us are chemistry teachers, all teaching various levels in the chemistry curriculum. Today's session will be designed as basically a conversation about how we teach chemistry with the next generation science standards in mind. Over the course of the presentation, we will talk about the evolution of the science standards document and ways that it has changed as a result of the public review process. We will also spend some time talking about the strategies that we actually use, realizing that not everything that we use is perfectly aligned with the current model of the standards. However, as a conversation starter, it's a great piece to actually get started with in terms of professional learning as a group or in general. The goals of today's session are basically to simply describe the standards, to highlight our practices, and to share some of the strategies that we use in a first-year chemistry class. That's an important idea because we realize that chemistry is often taught in 2 years at many schools, whether it's part of a Chemistry 1 and Chemistry 2 or a Chemistry 1 and an advanced placement chemistry program. We are simply going to be talking about the first year of a chemistry curriculum in a high school. So just to get started, I want to talk about the standards and the process of their development over time. In the 1990s, the American Association for the Advancement for Science published what was then called Project 2061. And it was in line with the TIMSS reports and other reports about the nation at risk for low performance in math and science. From there, the field of science education, and education policy came together to sort of better understand how we could improve science instruction. From there, the National Research Council participated in the development of a document that became a guiding document. And then over time, it has grown to become the next generation of standards, realizing that that was almost 25 years ago. So, along with Project 2061 and the National Research Council framework, states began adopting standards for science instruction. And what's really interesting about the next generation standards is that for the first time in at least my 20-plus teaching career, I actually see widespread opportunity for public review and discussion, debate, or feedback around the standards. Realizing that technology itself has enabled this process, it's a very interesting, layered, complex conversation. And so the science standards themselves are designed to focus on three intertwined ideas: science and engineering practices, cross-cutting concepts, and disciplinary core ideas. For this discussion, we will focus on the disciplinary core idea being in chemistry, which is a subset of ideas related to physical science. So here, this document, and I want to point out, you will be able to tell the difference in information because if it has this green banner, that means I incorporated information from the National Science Teacher Association, because the NSTA has been a guiding force in the development of the framework. So here is just another way of considering what I just described. The 1990s, you have the benchmarks in the science education framework. Lots of folks, states mostly, individual policy agencies began developing a scope until finally, in early 2010, the Framework for Science Education was published. In the summer of 2011, that initial document was reviewed, open for discussion in the same way that this document is up for review. So between July and now, January, we basically had various contributing organizations develop what's the next generation, and the review process is now live and open. So last week, January 8th, this new document was published, and it's open for review until January 29th, with the expectation that in March 2013, the revised draft of the Next Generation Science Standards will be published. So here are the three ideas that are intertwined in the development of the framework. And NSTA has taken time to actually show how the document has changed from the earlier draft in 2011 to the present. Notably, the addition of these appendices is a welcome difference, because it allows schools and districts to understand how they can design their own science programs that are well aligned with the goals and expectations of the standards. What I'd like to point out here is what the document actually looks like. You know that you've reached the right place when you see draft, watermarked. You actually see performance expectations in colored fields around those three intertwined concepts. And then at the top, you see a very clear description of what students will be able to do for each of the disciplinary core areas. So let's look at this one. Interdependent relationships in ecosystems, or environmental science, is a field in the life sciences. And so here we see a description of life science, and the 4D, 4E, 4A represent like a code that would describe what that additionally is. Another really important field in the document is the field that attends to the Common Core. Now we will see that very specific coding and language around language arts literacy and mathematics Common Core standards have been added to the document itself very prominently, so that as the nation moves towards the adoption of Common Core standards, it's part of this document as well. So, additional details. Group study topics. I put this here because the appendices become a really viable source of information if there are requirements or interest in understanding how to change a curriculum. So the appendices themselves, excuse me one second, the appendices themselves in the second draft show you how things have changed, the responses to public feedback. What is most interesting to me, however, is down here in J, K, and probably in F. So for me, if you were looking, for example, to design a curriculum or change the program from middle school through high school, here is a lovely example of how the middle and high school curriculum might look, or what it might look like. So I'm going to scroll on the screen, so I do apologize for that. But you'll notice that for various courses, you see PS, physical science, life science standards. ES also stands for earth science standards. So this document allows you to see what disciplinary core ideas in earth science for 3 courses might be, for life science might be, and for physical science might be. Okay? So now, to talk a few minutes about the organization. I said that organization of the Next Generation Standards is around practices, cross-cutting concepts, and disciplinary core ideas. So that begs the question, what are the practices that are most important? The spheres of activity is how it's described, and that is to investigate science. Students should be investigating. Science students should be evaluating, and science students should also develop explanations and solutions. So this is basically a tip and a nod to the scientific method and inquiry-based instruction the way it currently exists. What are the practices? Well, how does that translate? That translates in the science classroom as students asking questions, developing and using models, doing experiments, analyzing data, using math to compute and think about science problems, constructing explanations, engaging in arguments, developing arguments, and obtaining or communicating information. So there are several practices that many of us already do. Part of what we will talk about today is how we actually engage students in these various practices. So the cross-cutting concepts. Well, if you think about cross-cutting concepts as a bridge, and a rather bumpy bridge, it's not necessarily obvious that that's what's there, but in the beginning, you see one of the ideas that should apply across content domains would be patterns. The fact that we know science because we can identify patterns. So if you're talking about, for example, patterns on the periodic table, or you might talk about patterns of migration of birds, or you might look at patterns of stars over time and cycle, cause and effect, scale, proportion, and so on. These are all the cross-cutting concepts that no matter what class, no matter what content domain you're in, that is life science, physical science, earth science, or technology, you should be able to identify across the board these things in the curriculum. So what are the content domains? Physical science, life science, earth science, and engineering. What we've done here is our group of teachers has sort of functioned as a professional learning community. We've been looking at the chemistry curriculum as we implement the use of a new textbook. And we have highlighted in red those areas where we think as a program we do an okay job, but probably need to attend to this a little bit more. So the areas in red represent for our chemistry program, the three of us, as we design and implement it, how we can, or areas that we would like to reconsider and reimagine for our students. So physical science, I'll go back here. Physical science is basically broken down into these four categories: matter and its interaction, motion, energy, and waves. And so that would be true for both physics as well as chemistry. But if we look specifically at the context of chemistry, these are the areas. And when we look at it this way, we feel, okay, there's really only one area in the context of chemistry that we felt we needed to grow. And that was how we could use what we teach about waves to help students understand information technology and instrumentation. So what we use to teach. In a few moments, you'll actually hear from Linda and from Janine about what they use to teach, and the way that it's going to be organized is we are going to frame this by talking specifically about just theoretical models that are in place here at our high school, starting with this idea that quality instruction looks at students' level of understanding. First, do they have an ability to know what we're saying? Do they retrieve information? But building or digging deeper to the point where they actually own the information and can apply it, can connect it to other things. In our district, they're using Danielson's framework for teaching that actually helps us to think more broadly about how we're designing our lessons, how we are organizing our classroom, how we are actually delivering instruction, and then again, what is our role as professional educators in maintaining an environment where students learn best. So again, to focus on introductory chemistry, first year class. It's fun because in our department we have several people that contribute to our understanding about what we do. And one of our colleagues shared earlier this summer this great comment that just says, Heisenberg Department of Physics, you are probably here. So we actually thought about introductory chemistry, what we have in common. Whether we were looking at conceptual chemistry, college preparatory chemistry, or honors chemistry, all first-year chemistry classes are characterized by uncertainty for students. And so as they approach the class, it is oftentimes the most challenging course for them because this is the first class, potentially, where they have been asked to synthesize information from math and science and English and history in one course, because we do significant writing. We require independent research. We also use lots of math, and then of course the context of chemistry. So here you see a breakdown of the differences between the conceptual, the college preparatory, and the accelerated courses. You will note that all of us have a big ideas approach to the content, and all of us want students to actually make connections with the real world. But the main difference is the qualitative nature of the conceptual course versus the quantitative nature of the accelerated. Of course, there are other differences and ways for actually making the real world have more, or making chemistry have more meaning in the real world context. So that's what we'll get ready to share now. So we're getting ready to hear from Linda about the conceptual chemistry class. So conceptual chemistry, we call it chemistry in context, is...
And I can take over from, from here. So chemistry in context is, we break it into domains, and these domains are with regard to the large areas. Basically, we think of it as earth for the matter and materials, water for exploring solutions, air for chemistry and the environment, and then fire. We think of that as energy and nuclear reactions. And we also get into petroleum. So we bring up real-world problems and then have them solve it. And we use an evidence-based approach where they have several hands-on learning opportunities in a lab-intensive cycle of 2 labs per 7 days. And so the idea is that they will see the evidence and then from that come to their own conclusions. We also experiment with pre and post questions with regard to big ideas like conservation of matter. So what they come into the unit with, and then after doing several experiments, what they leave with, and then we make comparisons and collect data. So this is it's heavily lab intensive and looking at the big ideas for developing data, and from that data coming up with conclusions.
I think it's important to say too that the course, when it was conceptualized, the textbook chosen is the ACS chemistry in the community textbook. And so the goal of the course was to try to think about those students that struggle with math and struggle with the quantitative aspect of the course, and in doing so, give them a course that is more qualitative rather than quantitative. So that textbook lends itself really well to teaching in a context rather than teaching more in a traditional manner. I have to actually ask a technical question real quick. Dr. BJ?
Yeah.
You gave me your screen, but then the presentation went away. Is that because I had to have that open?
Possibly. I'll take it back.
Yeah, you take it back, and then I'll get that open, and then I'll take it. I'll tell you when you should give me the screen, and then I can show some documents.
Okay, sounds good.
There we
Okay.
go.
All right. So one of the things I wanted to talk about also is the implementation of a new course that is still considered conceptual. The new course is called Science, Technology, Engineering, and Math in the 21st Century Society. It is a problems-based course designed to be a physical science elective. So the focus is only on chemistry and physics concepts. So it is purely conceptual in terms of the design of the course, but the implementation has actually allowed me to really capitalize on some of the performance expectations for the next generation science standards. One of the tools that I use is actually ChemSketch. So ChemSketch is freeware. So I'm taking you here now so that you can actually see it's a free download with the caveat that there is no technical support. So for the first few hours of using it, it's a little bumpy because you have to play with it. However, it's really cool because it offers opportunities for students to sort of become familiar with a new type of technology. So what do we use ChemSketch to do? We build structures, we name compounds, identify isomers, look at structure-function relationships. And so when you get ChemSketch, and I will say that it works best in a PC environment. You can run it on a Mac if you can also run Windows on your Mac, but it's a really fantastic tool. So what it does when you download the program is it pretty much gives you a screen like this, which is like a Word document. You can choose the atoms that you want to use and then start creating various molecules, generate names, and actually identify different properties of the structures that you create. You can convert your alkane structures or your line structures, if they are not the most, I guess, efficient or in the proper tautomeric form. You can actually clean up the structure so that it is the more probable, and then convert it to a ball and stick, a space filling, or any type of structure that you would see. So I've actually taken heptanol and shown what it looks like in the 3D viewer for ChemSketch. So this is clearly giving students an opportunity to build and model appropriate representations, and it goes beyond the traditional ball stick model kits that we probably all have used in our chemistry instruction. So the college preparatory course is our chemistry one. So that would be our general ed course that satisfies high school requirements for most colleges. And here's our scope and sequence. So typically, over the course of a year, we do 10 units, starting with what is matter and how do we classify it, then moving on into the scientific method, then atomic structure, and so on. So one of the really neat things I want to underscore is in the earlier slide, hold on, I'll go back for a second. We talked about what students should do in their practice. So asking questions and engaging in argument from evidence. One of my favorite labs that we actually do with students is having them identify whether oobleck, cornstarch and water, is a liquid or a solid. And so the explanations, of course, are amazing to hear, but we also get an opportunity to sort of test out their research skills, which is why I say for a lot of students it's a challenge, because we hold them accountable for the quality of their sources, their ability to articulate ideas, and to develop reasonable arguments that are based on logic and evidence. So it's a really cool part of what we're able to do. So Linda and Janine, if you want to talk more about the college prep stuff. Or actually, you know what, before we do that, one other activity I wanted to share relates to a very familiar alien periodic table. So the alien periodic table that I actually used is modified here, and I used it with my textbook to actually teach the trends, periodic trends, and I added some questions. But what was really awesome about this exercise, sorry for scrolling on the screen, is I was able to go to the next level into predictions. So even if we go to this question 6, for example, we talk about one of the unknown metals, but then propose a symbol and a name for the missing elements and describe why you would have named it that way. So if you've got, how did I get to this? It's very funny because I actually got to this because, you know, this is a widely used activity for high school students, maybe even middle school students, and there are several keys and versions of this online. So I purposely changed some of the clues and added a few other pieces to actually get students to go beyond even what they find online. So these are all examples of how we're getting science or students doing what scientists do. The reality of it is most scientists start at some point in the 21st century with a model that they actually got based on something they found online, or at least that's how they check. Okay, so, all right, Linda and Janine, you want to say anything else?
So I think, good, Linda. Linda, can we hear you? Were you able to hear Linda?
No.
Oh, somehow Linda got muted.
So okay, now I'm unmuted. Okay, so I'd like to add on to the alien periodic table though first, because one of the widely used skills in the core standards is group work, and group work with regard to solving a problem together. And that was an example of splitting the kids into groups and then having them all take a piece, having them take a piece of each question, and then having the groups teach the other groups with regard to their thinking of, in the responses. So I wanted to add on to that. Then within Chemistry 1, we have units where we have an intermediate math level. So we are giving them the information, splitting it into, instead of functions like in chemistry and context where it's divided into functions, now it's more of a classical division of the procedures. But we have the students working heavily in labs where they have to rely on one another, and then they're each accountable for their own work. They communicate with each other employing Google Docs or Google Drive, and to share information but still be accountable. Janine, would you like to add?
I also want to say that we, as a PLC looking at implementing this new textbook, have talked a lot about how we would get students to interact with text and interpret text, and I think the purpose of the alien periodic table was to also have them interact with text in a different way and make decisions about recognizing patterns. And I think that specifically in chemistry, when you look at electrons and atoms in the periodic table, that's a great place for that cross-cutting concept to come in, where you're asking kids to recognize trends and using the periodic table itself as a document for students to learn to really analyze text and use the periodic table as a text. So I think that we've tried to highlight that cross-cutting concept specifically in this unit that we have been working on together. And I think also what we have been trying to do, like I said, is introduce nonfiction text, especially if you think about the Common Core. Some of the focus of the Common Core is asking the students to improve their nonfiction reading and writing skills. And one of the things that I have specifically experimented on last year and plan to experiment on this year, not only in the honors course, but in the college preparatory course, is reading Napoleon's Buttons as a nonfiction text. Dr. BJ, is there a way for you to give me the screen? So I got the project outline to share with all of you of the project that I developed with Napoleon's Buttons last year. I don't know how many of you are familiar with the text, but this is something that I've specifically been thinking about, knowing that the students do not read as much as they should these days, and knowing that they have a very hard time. Let me see if I can get this now. Let me see. Oh, Microsoft has encountered a problem. I don't know what you guys are seeing and what you're not seeing, to be honest with you. Let me see if I can get this back up again now. The joys of doing a webinar for the first time and using the technology for the first time. Where did it go? There it is. Can you all see this, or is it covered up by all of my webinar materials? Wait, oh. Can you see it? Okay, great. Oh, man. Even though my screen is going crazy. Okay, so this is my Napoleon's Buttons project outline. And so what I did was, last year was, I chose a few chapters out of the text for the students to read. So specifically, the premise of the book is that 17 molecules that have changed the world. So you look at the historical context of the molecule, the discovery of the molecule, or how it has influenced history in some way. So we looked at glucose, we looked at, what else did we look at last year? We looked at morphine and nicotine and caffeine, we looked at salt, and I had the students read the chapters. And what I didn't do well last year was actually have the whole group discussion about each of the individual chapters in class, which is something that I would like to do this year. And then if you look at the rubric, I've split the students, the class into groups of 4 students and assign them a molecule. And they specifically had to put a PowerPoint presentation together to essentially build upon what was discussed about the molecule in the textbook, in the text. And then I had them build also a 3D representation of the molecule to present to the class. And so this was a way for me to try to bring in some nonfiction reading and also highlight things like the historical, evolution of science, thinking about how these scientists made these discoveries, came up with some of the processes for even making some of these molecules on a mass scale, and essentially give some of the students real-world applications for chemistry in their lives. And I found that they really actually enjoyed the project very much. So this is one of the ways that we're trying to kind of extend and bring in Common Core and the next generation science standards into the classroom. The only problem with doing things such as this is that it takes time. It takes time out of the class, and so I find it extraordinarily hard to find time to do it in my honors class when the end goal is for the kids to take an SAT-2 at the end of the year, and thinking about the content that you have to cover and kind of finding a balance between doing things like this that really do align well to the standards and give students valuable skills and still, try to cover content. And I guess that's every teacher's problem. So just another example of what we're doing.
Right. I wanted to take a few moments and jump in and answer a few questions while Janine works some of these things out. So I will read the question and give some of the answers, okay? So what are some of the nonfiction texts that you use? We actually have used not Napoleon's Buttons, Disappearing Spoon, but we also use things like the New York Times. We use plenty of resources from EBSCO as real-world articles. Last year's Japan nuclear meltdown is a popular source of articles now as we develop more more materials to address informational and non-fiction text. Now, the textbook that we currently use is Tro 4th edition, Introductory Chemistry, but we have also used Zumdol's World of Chemistry in the past. Does the college preparatory class use ChemCom as well? I wouldn't say that we use ChemCom as a guiding book. However, there are some activities that are just strong activities, demonstrations also that are just really fantastic demos that are outlined in ChemCom and the ChemCom materials. Remembering that ChemCom is an ACS text, it has really very well done resources. In terms of sharing assignments, absolutely. If you're referring to the, well, answer or ask the question again. Which assignment would you like? And
if it's the Napoleon's Buttons assignment, I would be glad to send it to you. I think that if I continue to scroll down here, I developed some rubrics, and I would even be willing to, I haven't made changes from when I implemented this last year, so I would even send the edited drafts once they are done. You always do something one year, and you learn an infinite amount about what the students will do or will not do. They always surprise you. So I will make those changes and I will send them off. If I can, I'll find a way to do that. How have you done that in the past, Troy?
Okay, good. Well, in the past, I have actually just made everything available as part of the PowerPoint, but I haven't had to use, I haven't used this. So I haven't actually described, for example, specific assignments. And so this is cool.
Joy, do you want to go back to the PowerPoint and talk about SET, and then I can talk a little bit about Google Docs, or do you want me to do Google Docs?
Let's do that. Let's go back to the PowerPoint and get that back and running. Can you bring it back up, Mrs. Giamenko?
The presentation?
Yes.
No, listen, the PowerPoint presentation, I couldn't show the Google Docs later on if I had my other Google open. So that's why you just switch to your screen, and then we'll come back. Sorry to everybody for the technical.
No problem. Okay, so let me answer a few more questions first. So in the the lower level course, there is qualitative material. However, there is more conceptual. It's not even more theory. We talk about how the information is applied more directly. We use math, but it's not to the extent, we do not hold them accountable to the same extent that we hold other students accountable in the higher level courses. And I'll take one more question. Are ChemCom students expected to take an end of course exam from the state? We actually don't have those yet here in New Jersey. So Yeah, yay. Not yet. So we probably would, however, hold them responsible. Our biology students actually do have the responsibility of taking the end of course test in biology, and so yes, we probably will hold them responsible as well. So I'm going to switch back to our session and share some more of the tools that we use. So I'll start and then I will defer back. Okay, so in our college prep course we actually use PhET and Explore Learning, if you're familiar with them, as simulation tools, and very popular with our students, or maybe not, the learner.org series actually has the World of Chemistry online, which is fantastic. So I brought you here so that you could actually see how to get that. You would go to learner.org, which is a public broadcasting resource, and go to World of Chemistry. When you search for World of Chemistry, the list of resources come up. You can see the cost. This is the cost of the book, but the videos that are available as 26 half-hour videos online. So the descriptions of the videos are here. So one of my favorites, for example, is actually Chemistry of the Earth, which allows me to bring in some of the details for chemistry and earth science, since many of the students in our chemistry program actually take it as 10th graders. They took biology as 9th graders and may never take earth science. So the VOD highlights the on-demand feature, which, hold on, as you can see, you can then show all of the videos and stream them online.
Additional funding
So
provided by the people of Dow.
one of my favorite things to do also
The 8,000
includes,
scientists of the Eastman Kodak Company. The
hold on
Exxon
one second,
Education Foundation
after you
on
get through
behalf
the
of Exxon
commercial,
Scientists and
is actually to put on the closed caption so that students that are in the ESL population
Look at any corner of our planet, and it looks like it's been there forever.
can actually
But the
begin
Earth
to
is
read
dynamic.
the
It's
resources.
been continuously changing.
Okay?
The great part of that, too, is because it is streamed online, if a student is absent from class, you can email off the link and the student can still watch the video because it's online. So that, I think that's a really good resource. The videos are a little bit older, so some of it is a little bit dated, but overall, very, very good stuff.
Okay. So popular movies that we have used include some that were as fun as the Revenge of the Nerds, which I love the Lambda song. No one seemed to get that, but Revenge of the Nerds, Terminator 2, yeah, those are the two of my favorite. And then we've also used PBS videos. Einstein's Big Idea and the Absolute Zero were two of the ones that we currently circulate.
And Hunting the Elements as well.
Oh yeah, I forgot about that one, which is fantastic. So okay, other tools that we've used are Explore Learning. Now, Explore Learning is a subscription service that must be paid for. However, it has fantastic simulations, but then there's this free version. PhET is a resource that we also use quite often, and so Linda and Janine can talk about that, and I'll pull it up.
So I use this resource all the time for various different, to teach various different concepts, and it's great to use it to put together an interactive online activity for the students for a lab such as if you're trying to show alpha decay. And you're in a nuclear unit. It's very hard to come up with quality, hands-on lab activities. These simulations are absolutely fabulous. They illustrate the points to the students very clearly, and you can even do almost like a inquiry-based activity where you have the students make observations and then answer questions and kind of come to conclusions on their own, or they're great to use as essentially demonstrations. So I was just talking about, we were doing solubility rules, and I was talking about insoluble solids earlier today. And if you scroll down, there's even a solubility KSP simulation. And so you can use this to simply show the dissociation of ions in solution and to show what it means to be an insoluble solid, or you can put together a much more complex activity for a higher level class, and you can have the students design a salt and look at the KSP. So these are really versatile, and I also believe they have some lesson plans online as well. If you search for them, and they're pretty good.
All right, let's move on. So we also have in the shoes of an engineer. Oh no, I didn't log out. My bad, excuse me. We'll share that as well, which actually is a description of a program that we did with a local university where engineering students came in and worked with our students. Linda, you want to talk about that?
Sure. So we're associated with, we're in the town of Princeton, and the university students at Princeton came and acted as if our class was a third world country. That is, they did all of the kinds of activities that they would do in going into a third world country and helping to assist those individuals in solving the problem. So they first brainstormed with the students of what are the possible problems that the students would see with the facility, and then they narrowed it down into a topic, and the topic that they came up with was roofing material. I'm trying to click on this to open it, however I'm not able to. I'm not sure if you're able to, Joy, to show the activity that we did.
Yeah, it didn't open for me, so hold on, I'm going to change to you. Hold on. Okay. Now see if you can open it.
Okay, through my, okay, I'll see what I can do here. So when we, so in speaking about it, I don't really feel comfortable with having all my, like I don't have right here handy. But I'll just speak about what we did. So we had the when the engineers came into school, it was very exciting for the kids because they got to see that engineers were not just people with pocket protectors, but were real people who we designed a little project too, where they were the class was split into two groups, and they each had to sell their own aspect of what part of roofing design would make the most sense and be the cheapest. So they split into roles of chief engineer, salesperson, and safety. And
I'll take your screen. I'm getting this up since I don't have the PowerPoint. Okay.
So then they had to present their argument to each other to win the bid. So okay. They were actually conducting the work of an engineer by doing. So problem solving by doing. It looks like the accelerated screen is up. Is that?
Oh, that's me. Okay, so we figured that we would finish with our, so like I said, we had three different levels of chemistry. So we figured we would finish by talking about the honors course, which I teach. And if you compare the honors course to the regular college prep course, we get about here in our regular college prep course. And in terms of solutions in our regular college prep course, we obviously talk about molarity, and we talk about saturated, unsaturated, supersaturated solutions. we do not talk about things, and we briefly talk about colligative properties. We get a little bit more into vapor pressure and colligative properties here in the honors course, and then these are essentially the topics that we get to beyond what we would do in Chem 1. So we move significantly faster in this course, and I would say the greatest difference is that we not only move more quickly, is that we go into significantly more depth, and it is more quantitative. And what I've really tried to do with this course is to highlight a lot of student collaboration and interaction in terms of gathering data, sharing data, and writing about their data. And what I found to be extraordinarily useful, which also cuts down on a lot of paper for me, but it's been very valuable for the students and for me, is the use of Google Docs in doing their lab reports and other assignments. So I just wanted to highlight that for you. So this is a lab report that the students did. I should have probably taken those names off there. So this is a calorimetry lab, which the students had an unknown metal, and they had to take their metal sample and put it into boiling water and wait till thermal equilibrium was reached, and then put it into essentially a coffee cup calorimeter and get the equilibrium temperature of the water and then perform the calculations. And they did this in teams of 2, and then they had to identify their unknown. And so what I've experimented with doing is having the kids work on joint lab reports. And the problem with joint lab reports in the past is that you had absolutely no idea who was writing the report and how much of the report was being done by one student versus another student. And so Google Docs really eliminates that because of the feature where you can go to File and see revision history, and then the revision history will come up on the side, and then you can see who has worked on the document and when they had worked on the document, and you can see how much collaboration has actually gone on. And what that really has allowed me to do as well is, as they're working on the document, it allows me to leave them comments all along the way if they ask me to, and then I can simply grade their lab online. So, and I've kind of worked out with them little things like, if I highlighted in red, it would be maybe a typo or some word that I may have not used. I can highlight whole passages and leave them comments, such as the one that you see over here. And then in the end, when I go to grade it, I just copy and paste a rubric right into the bottom and then give them their grade. So, and I can do things like this, which is always fun to do if they did a really good job. But this has saved me a lot of time. You essentially, obviously grade half the papers, but I found that I end up looking at a lot of their labs ahead of time. If they ask me, can you please look at it, see if I'm on the right track, make a comment about this. So maybe in the end I'm doing the same amount of grading, but I think it's far more productive grading. And I think the students learn that, like real scientists, a lot of the papers that are published are written collaboratively, and they learn, to learn from each other and improve each other's writing along the way. And it's really fun to see how much their writing improves by doing this. And you can use Google Docs for all other different kinds of assignments. I also use the forms function. Let me see if did I get up a form? I still have that out. Let's see. So this is a homework assignment that I just put together, and now I have to see forms, go to live form. So the students would see it like this. So I give them a link to the assignment, and all they have to do is essentially type in their answers and click submit, and then it would go to this spreadsheet. And what would come up would be the student's name, first name, last name, period number. I can sort by period number, and I can look at, essentially can just scroll across the spreadsheet and look at some of their responses and give them a grade. So I've used Google Docs in all different kinds of creative ways to essentially help the students get some more productive immediate feedback and kind of focus on this idea of collaboration, collaborative writing. So just wanted to show you this as well.
So I wanted to take a few moments and field a few more questions as we are approaching the 5 o'clock hour. I'm going to take the screen back from Janine. And
thank you.
Hold on, give me a moment, and answer a few of your questions. Some of your questions are really amazing, and I wanted to make sure that we talked about them. So, but first, Annenberg is making a new World of Chemistry series. Yay. So that's exciting. Now, the question about the engineering, there was a question about engineering activities in the chemistry curriculum. Admittedly, this is a growth area for us, but thinking about building molecular structures, especially for designer molecules, is one way to conceptualize that, but there's work to be done here. Another question is about creating a folder online that we could put some of these documents in. I will work on that and try to communicate that through the organizers to make that happen. So the other thing I do want to take a moment to talk about, though, is the Common Core and the connections to the Common Core. So the college readiness standards, which in defining college ready as is defined by the ACT, we're looking at students being able to go to college ready without remediation and have success. And so the Next Generation Standards has actually been very good at pointing out how developing these habits in students will get them ready for that. But I want to take you here one more time to actually show you the response. So in these appendices, in the appendix, for example, C, there is specific attention to the college and career readiness framework that will be implemented in 2010. So here's additional information about the background, but hold on, let me scroll down quickly. There is, I can't go fast when I'm on the screen, so hold on one second. In the document itself, there are just they're pointing toward it with the understanding that getting I won't do that in the interest of time, pointing to it so that everyone begins to understand how. So if you go essentially to all standards, all science, and the core idea progressions, you start to see. And so scrolling down here, this is basically your go-to place. That's the end of the story. This is your go-to spot, and actually seeing how we can get students ready, moving them from the lower grade progression through high school and into practicing and thinking like real scientists. It is a little after 5. I wanted to thank you for your patience with us as we go through this together, and answer any additional questions can be emailed, I suppose, to me at drbjscience@gmail.com, and we will forward responses as appropriate. Thank you very much. Have a great day.